Hi, this is Ms. Carnicella, and we're going to go over higher order derivatives. So let's get started with an example. Since there are no students in the room, we're just going to go straight to it. We've started out talking about derivatives. Let's say we have a function f of x is equal to 3x to the third. If I wanted to take the derivative of that, I would just go ahead and use the power rule, and that would give me 9x squared. But you can take the second derivative, and that would be a function, because if you take a derivative of a function, you get a function. So the second derivative of that, I could take two. I could go ahead and keep going. You could take the derivative of a derivative, and that would be 18x. Why is this important? Well, when we're talking about rates of change, or we have a position, a function that's in a position, let's say, instead of doing all the math to find the velocity and the acceleration, if you just take the derivative of that position function, you're going to get the velocity. And if you take the second derivative, so if you have that one and you take the second derivative, you get the acceleration of what that object is moving at. And that's why we're learning how to do this, because it becomes more of a shortcut in finding velocity and acceleration of an object. We saw that. And let's just go ahead and go through some examples. Let's say I have h of x is equal to x squared cosine x. Now, I'm going to talk about really quickly some notation. You might see for the first derivative, so you might see something like f prime of x. That's the first derivative. Or then they'll say f double prime of x. That's going to be your second derivative. And then there'll be third derivative. There'll be three little notches like that for the third derivative. And then after that, they just write the number. So it'll be like, take the fourth derivative of x. Or it'll say from then on, it'll just tell you the number. But there's also other ways to write these. You might see y prime of x, y double prime of x, or not of x, just y double prime is how they'll write it. Hold on. I'm getting a message on my computer. Give me 1 second. Let me get this off. Okay. And some other ways that you might see this written. Let me give myself some room here. It might be written like, that would be find the derivative. Find the second derivative. Sorry. Might look like this. Third derivative might look like this. So just letting you know that there's different notation that you're going to see. But in this one, I want to see how many derivatives I can go. So what I'm going to have to do here is use the product rule, because I have this times this. So the product rule is, if I have the derivative of f times g, that's going to be the derivative of the first times the regular, just g. And I'm going to add just f times the derivative of the second. So in this case, I'm going to be getting is equal to 2x times cosine x. I'm going to leave that one alone. Plus, now I'm going to leave the first one alone and take the derivative of the second one, which is negative sine of x. And I want to write that nicer. So I'll put 2x cosine x minus x squared sine x. But if I wanted to take the derivative of this now, why does this keep coming up? Give me 1 second. Let's just keep going. I'm going to go ahead and got to work on this one and use the product rule. So that's going to be 2 times cosine x plus 2x times negative sine x, right? That was all this. I had to use a product rule, minus 2x, I'm taking the derivative of this one, sine x, plus, now I'm going to take this one, leave it, and take the derivative of this one, x squared cosine x. And let's make it look prettier. That's going to give me 2 cosine x minus 2x sine x minus 2x sine x again, minus, don't forget to distribute out that minus, x squared cosine x. So what I would want to do here is collect these like terms because they're the same, and then I just rewrite it. So that's going to give me 2 cosine x minus 4x sine x minus x squared cosine x. And that's my second derivative. And you could take the derivative of this again and then just keep going, but we're just showing you right now. Maybe I could draw a better square than that. But we're just showing you that you could take the derivative of a derivative, but you have to use your product rules, your chain rule, whatever you need to do to take the next derivative. All right, let's go ahead and look at another example. This is more, it's going to be more straightforward because as it turns out, we're lucky with e to the x when we're taking derivatives because it doesn't change. So if I wanted to take the first derivative of this, I would use the product rule, which is, the power rule, which is 12x to the second. But e to the x is always e to the x, so that would be minus 3 e to the x. That doesn't change. If I wanted to take the second derivative of that, I'd go ahead and use the power rule again, multiply, which is really this. I'm going to write it out for you. 12 times 2x to the first power, just in case you didn't trust my first one, e to the x. And then that would equal 24x minus 3 e to the x. All right, so I just wanted to check that, make sure it's good. 12, so that would be 24x, okay. So why do we do this? Let me just really quickly give, since there's no students here, I'm going to run it by quick. Just say you have this function. And you have a graph that is telling you the position of the function. So let's say something's launching and you launch a rocket and it goes up into the sky and then it comes back down. All right, that right here is the position function. This is telling you at each moment in time where it is. Okay, so and 1 second, I mean at 0, it's nowhere. And then at time equals 1 second, let's say, this is how high it is. And it gets all the way up to this point where it just can't go anymore. All of a sudden, it changes direction and starts coming back down to the ground. So this is going to be the position of an object. Let's just say, I'll put a cannonball. Okay, that's the position of the cannonball. Once I find the derivative of that function, whatever this function is, we'll call it S of t. That's where it is. That's the position at any time. Once I find the derivative of that, now I'm finding at this time, what is the velocity? How fast is it going? Okay, so all I have to do is find the derivative, and if I wanted to know at time, any time here, I could plug in that time, like 5 seconds, and it would tell me the velocity at 5 seconds. And if I took the derivative of that, I would know what the acceleration, how it's accelerating. Acceleration, I can't fit it, but acceleration. And that's why we're taking these higher order derivatives. So, give me 1 second. So let's just take something like, what if I said find f of x is equal to 3 square root of x plus 5x. And I'm just giving different examples, so you see you have to mess with them a little bit, because I would rather write this as 3x to the 1/2 power plus 5x. If I wanted to find the derivative of this, I'd use the power rule, so it's half times 3, which is 3/2. X, a half minus 1 is negative 1/2 plus 5. I'll use it. I'm using the sum rule here too, and just finding the derivative of this and the derivative of this. So if I wanted to take the second derivative, I'd say negative 1/2 times 3/2, that's going to be negative 3/4 x, and negative 1/2 minus 1 is negative 3/2, because you always minus 1. And now you don't even have a constant anymore. I could find the third derivative, and that would be just positive, I don't have to write the positive, you know it is, 9/8 x to the negative 5/2. And just a little something that you might see on your mastery test. If it said y is equal to x to the n power, and it asked you to find the derivative of y, okay, so let's say it said find the derivative of y, you're going to go ahead and just use the the power rule first. But then if it says find the derivative of y prime, well, now you know that you're going to multiply this in the n minus 1 times the n. And now you'll have n minus 1 minus 1, which ends up being really n minus 2. And if I wanted the third derivative, well, I'd have this n times this n minus 1. But you got to multiply it times this n minus 2 now, because that's your power rule. And you'll be left with x times n minus 2 minus 1, which is n minus 3. So that might be a mastery test problem you'll see on this section. All right, so we have this question. The distance a driver travels on a mountain is given by the function 3t to the fourth. So I'm going to rewrite it here. 3t to the fourth plus 2t squared plus 4. What is the acceleration after 2 minutes? Well, the distance means that's position. So that's like your s of t. All right, so at time t, let's say time is 1 hour, whatever they're doing it by. So I'll say minute. Okay, so at time, let's say 2 minutes, I would plug in 2 here to see where exactly it is from that starting position s of t. But they don't want the position. They don't want the velocity, which is the second derivative. They want, I'm sorry, which is the first derivative. They want the acceleration, which is the second derivative. Okay, so that's what we got to work towards. So I'm going to go ahead and find, because to get to the second derivative, I got to find the first derivative. So I'm going to go ahead and put 4 times 3 is 12 minus 1, that's 12t to the third, plus 4t plus 4. That's my velocity function now, right? Oh, 3t to the third is what I meant to put. It's not going to matter. Is it going to matter? No, I think it's fine. We'll just do it this way. All right, so then what you're going to do now is given by this, we found the derivative. Just check me, make sure I did everything right. 2t. Okay, so now I'm going to take the derivative of this and I'm going to plug in 2 once I'm finished. So that's 36t to the second plus 4. So if it said, what is it going to be after 2 minutes? Oh my gosh, I hope it makes sense. It's not going to make sense, I don't think, but we'll do it over. That's going to be 36 times 4 plus 4. He's going really fast. Let's just redo it. This was supposed to be all right, let's just redo this. Okay. I put it in here wrong. So let me fix that. This should be to the third power. And I'm sorry, that was fine. This should be to the third power. So let's redo it. All right, so his function is really given by 3t to the third. And what I did was, it works, but it just doesn't make sense that anybody's going that fast, that they're accelerating that fast. So I just want to redo it so it's more logical. All right, so now let's redo our first derivative, and that's 9t squared plus 4t. Now, if I wanted to know the velocity at a certain time, I could plug in that time that they give me. But they want the acceleration. So that's going to be 18t plus 4. And they want the acceleration at t equals 2 minutes. So I'm going to plug in, because that's acceleration. I gave myself the formula for acceleration. And that's going to give me 36 plus 4 is 40. And I don't know what the unit is, but we'll put units per minute squared for the acceleration, per minute per minute. So the last thing I just want to go over is Galileo. Oh, I hope I'm spelling his name right. Galileo. Observed the position of an object after a certain time. He observed it to be whatever that time was squared times 4.9. So he discovered by just observing that the position of a free-falling object, I should have said that, was 4.9 times whatever the time that it had been free-falling is squared. From there, you can take and find out the velocity of that object, and that's by taking the derivative. So that gives you 9.8 times time. But we get that number that we see all the time for gravity of acceleration, 9.8 meters per second squared, I think it is. That 9.8 comes from this original observation that Galileo made. Next week, I will be going over how to tell by functions which one's the second derivative, the first derivative, or the original function. Until then, be great. And I did forget to tell you, if you have any questions, please reach out to your teacher.